This is Unit 1B. It deals with energy, heat transfer and insulation. Now in the top half of the slide we have 6 different materials that we're interested in, and on the left hand side here we've got metal, free air and water, and they're all good at transferring heat. On the right hand side we've got wood, trapped air and a vacuum that are all bad at transferring heat, and we refer to them as insulators. Over here on the left we've got 3 processes. We've got conduction, which is particles crashing into their neighbours. We've got convection, which is the flow of fluids due to heating and density changes. And we've got radiation, which is waves transferring energy. So let's look at each of these in turn and see why they are good or bad at transferring heat. Now, metal is very good at transferring heat via conduction at any rate. The reason for that is the free electrons, which we can see here flying about. Can't have convection because it's not a fluid and not much radiation is going to get through. Then we've got free air. Now free air is a conductor, a very poor conductor, so we call it an insulator, but it can conduct a little bit. It is however very good at convection, and we rely on its convection properties, and sometimes that's very useful. Radiation will also get through air reasonably easily. Then we've got water, which is actually a good conductor, although the effect of convection usually swamps that, and not a great deal of radiation is going to get through. Then we've got wood, which is a insulator because we can't have convection because it's not a fluid. We can't have much radiation either, and we're only going to get the poorer form of conduction, which is not aided by free electrons, so it's a good insulator. Trapped air is one the examiners really like to ask you about, and it's really important you understand what's going on here. So the only process available to us is conduction, but it's a very, very weak form of conduction. As we said, free air is not very good at conducting. We also have completely shut down the convection because although the particles are moving in their tiny little trapped spaces, they can't move around as they do in a proper convection cycle. And finally we have a vacuum, and the first two can't operate in a vacuum because they both require particles, and there are no particles in a vacuum by definition. So let's look at convection in a little bit more detail. It takes a little bit of understanding. We have got 2 situations here. First situation, we've got cold 3 particles, and here we've got hot 3 particles. So the mass, 4 particles. The mass hasn't changed, but the volume has, because the temperature has. So think of 4 people, they start dancing vigorously. Imagine there's a big elastic band around them. That's going to expand. So we have more heat, greater volume, and if we look over here, if we have an increase in volume, so the volume becomes bigger, the mass stays the same, we're going to get a lower density, and this arrow represents that idea. And density is mass per volume. And because of that, we're going to get an increase in buoyancy. So whatever it is will float upwards. So we've got here, hopefully we can see an area of lower density that's being heated at the bottom, and likewise in the water. Let's have a look at the next slide. The next slide illustrates an application of these ideas, really. So we've got 2 houses here. We've got the house on the left that's not very well insulated, and the house on the right that's very well insulated. So it's got things like carpets, cavity wall insulation, double glazing and loft insulation there, a lot of which rely on trapped air, which we mentioned earlier, which as I said the examiners are very keen on. So the trapped air is a very, very good insulator because we can't have convection and we can't have any conduction or much conduction. Over here we've got some insulation, but it's kind of inherent in the building materials. We could do a lot better over here. Let's go back to our basic concepts. So we've got matter and we've got energy. Dealing with matter, first we've either classified them as insulators or conductors, and as we said, insulators are poor at transferring heat, conductors are very good at transferring heat, and insulators therefore save money because heat costs money. Now how much money it saves you or whether it's a good idea is illustrated by the concept of payback time. So let's have a look at that in a little bit more detail. So imagine here the blue line is the left house here, and it costs £250 a year in fuel costs. Now we could choose to spend £1,000, and so on day one we are down £1,000, but from then on our fuel bills are only £50 a year. So difference between those two figures is 200. So of the £1,000 that we spent, each year we chip away at it, and it would take us 5 years to break even, which is this point here. From then on, the red line, which is the total cost of insulation plus fuel, is lower. So if we're planning to stay for more than 5 years, it's a good idea. Now over here we've got one of the most fundamental statements in science: energy cannot be created or destroyed. And we can illustrate that in this little diagram here called a Sankey diagram, where the size of the arrow indicates the amount of energy. Now my example here is a TV. TV produces heat, sound and light. Sound and light we want, heat we don't actually want. This is an important concept for engineers. We need to know the efficiency. So efficiency is useful over total. So we've got 40 is useful over the total of 100 supplied. So we think of that as 0.40 or 40%. So 40% is useful. So that was Unit 1B, heat transfer and insulation, where we considered how we represent heat flow and energy changes, and we think about the costs.